So it's Tuesday, May the 5th, Cinco de Mayo, and we're here to talk today about general chemistry for Northern New Mexico College, and we're here today to talk about common ion effect and hopefully get initiation into buffers also. Okay, so now that we have talked about the pH of salt solutions, we are prepared to talk about common ion effect. So what is common ion effect? Okay, common ion effect is when you have an ion in a solution that comes from two different sources. So this can come about from mixing a weak acid, which we know will dissociate to give us some anion. But then in there, we can also put some salt solution that contains the same anion as is obtained from dissociation of the weak acid. Okay? For example, if we were to mix acetic acid, all right, now when this reacts with water, we're going to get hydronium ion and acetate anion. Run out of room there, acetate anion. However, if I were to mix that with a solution of, say, sodium acetate, all right, when I put that into water, it dissociates. This is a strong electrolyte solution. Both sodium and acetate anion dissolve with no exceptions. So I'm going to get sodium cation plus acetate anion again. So we can see that in this solution, if we mix acetic acid with sodium acetate, we're going to get two contributions to the concentration of acetate anion from both the weak acid and from dissociation of the salt. Okay, so we want to be able to calculate concentrations of all the species in solution. We won't worry about the concentration of the sodium. Actually, we'll know that since this is a strong electrolyte, the concentration of the sodium cation will be whatever the concentration of the sodium acetate solution is. Okay, since that completely dissociates. So we're more interested in calculating at equilibrium the concentration of the free acid, the hydronium ion concentration, or in other words, the pH of the solution, and the concentration of the anion here. Okay, so the common ion in this instance would be the acetate anion. So let's see here. Let's take a look at, again, you can take a look at the example. I won't do that since it's all worked through. We'll take a look at the corresponding exercise. And I believe it's numbered. Now, this is probably going to take a few whiteboards here. Okay, so what is the concentration of formate anion in a solution at 25 degrees that is 0.1 molar in formic acid and 0.2 molar in HCl? And we want to know what is the degree of ionization of formic acid. Okay, so formic acid is, I like to write it like this, so I'm going to write it the way I usually do, plus H2O gives us H3O plus formate anion. All right, and we're going to set up an ice table here. So let's go ahead and do that. And we're told the initial concentration of the formic acid is 0.10 molar, and the concentration of hydronium ion from the HCl. Remember, the HCl, the hydrochloric acid, is a very strong acid, so it completely dissociates in solution. So this is going to be 0.20. And of course, the formate anion will be 0. Right? It will be 0. Right? So what is going to be the change at equilibrium? Well, some of our formic acid is going to dissociate, so we're going to lose X amount of that. All right. Now, when this dissociates, it gives us hydronium ion. We already started out with +2, but now we're going to add some hydronium ion from dissociation of the formic acid. So I'm going to write +X here. And of course, for every molecule of formic acid that dissociates, you get both a hydronium and an acetate anion. So I'm going to write +X there, +X. Okay, and then at equilibrium, we just add the two together. So 0.10 minus X, 0.20 plus X, and plus X. All right, plus X. So there's our ice table. Again, if you can get to this point, if you can construct the ice table appropriately, you should have no problem answering any question that follows. Right? No problem. So we can set up an expression for the equilibrium constant. And to do that, I'm going to get out the other big board here. Does everybody have that ice table copied down?
Yes.
Okay. So let's take a look at expression for Ka. So Ka equals hydronium ion concentration times acetate, or formate ion concentration divided by the concentration of the free acid. Okay, now we're just going to plug in the numbers here from our ice table, right? So Ka equals, the acid was 0.20 plus X, the formate ion was just X. And here, the equilibrium concentration of the free acid is 0.10 minus X. Okay, now this looks like a quadratic. We're going to have an X times X term here. Okay, so we want to do that little Ca divided by Ka and see whether or not it's bigger than 100. If it's bigger than 100, we can disregard the X, the plus X, and the minus X. And our quadratic becomes a very simple problem. It turns into a linear equation. So let's go ahead and do that. So let's see, we need the Ka for formic acid, which we have to go back and look in the table on page 547. It is one. Now.
There he is. There he is. Wait, Raymond.
Yeah.
Raymond.
Yeah.
We didn't see where you did the CA because you were frozen for a long time.
Wi-Fi disconnected.
All right, thank you for letting me know that. So were you here for this part right here?
Yes.
We just plugged in the values from the ice table. Let me get a pointer here. Let me use my back scratcher as a pointer so I don't keep casting a shadow on the screen. All right, now we want to test whether or not we can drop this minus X and this plus X. Otherwise, we're going to have a quadratic equation, which we're trying to avoid, hopefully, right? Not that it's hard to do, but it's a bit tedious and cumbersome. So we have this little test that we saw earlier in the chapter. If you take this starting concentration of the free acid, the formic acid, which was 0.1, divided by the dissociation constant for the acid, which looking in the table, okay, earlier in the chapter is 1.7 times 10 to the negative fourth for formic acid. Divide those two, I get 588. Now, if that's bigger than 100, remember, we're justified in dropping these X's here. All right?
Right.
So our quadratic becomes a linear equation. All right? So again, if that's bigger than 100, then it can be shown, although our book never does it and we're not going to spend time to do it, that our error in our final answer is less than 5%. Right? So we can live with less than 5% without having to do the quadratic equation where the error would be 0%. Okay, so let's go ahead and do this. I'm just going to rewrite this equation and getting rid of the plus X and the minus X. So our quadratic becomes a linear. Okay, so there we go. Now we want to solve this for x. So 0. Actually, I'm going to pick a different color because everything is going to run together here. So it'd be nice to have different colors. 0.10 times Ka divided by 0.20 equals x. All right, so let's see, I'm running out of room here. Let's see, I don't need this up here anymore, so I'm going to erase that. All we had to prove was that was bigger than 100. So I'm going to bring this up here. We have this whole half of the board to work with now. Okay, so let's see, x equals, I'm going to flip that and plug in the value for Ka. So 0.10 times 1.7 times 10 to the negative fourth divided by 0.20. Okay, so that looks, we don't even really need a calculator for that, but we'll do it anyway. So x equals, so 1/2 of 1.7, that's going to be 0.85 times 10 to the negative fourth. 0.1 divided by 0.2 equals times 1.7, double negative. Second scientific, so 8.5 times 10 to the negative fifth, and I'm going to write an M for molar. So that is our concentration of formate anion. And again, what were we asked to calculate here? All right, so we're asked to find the concentration of formate anion. So there it is. All right, and again, I have this problem worked out. Yes, so that is the correct answer. Okay, everybody see what we did there? Okay, the main thing again is we just tweaked our ice table a little bit. Okay, so the starting concentration, usually we have some starting concentration for the free acid and the free base, and then the products are usually both 0. But since we mixed two solutions together, okay, we mixed formic acid and sodium hydrochloric acid, the starting concentration of the hydronium ion is not 0, right? It's whatever the concentration of the hydrochloric acid was, right? So then we set up our equation for equilibrium constant, okay, using the values from the ice table, and we did our little test to see whether or not we were justified in dropping the plus and the minus x. Okay, so that's the first. So we've answered the first of the two questions. Remember, from the ice table, x is the concentration of formate anion, right? So that was the first question we were asked to solve for. The second question is, what's the degree of ionization, right? What's the degree of ionization? So the degree of ionization, does everybody have this? I can erase it?
Yes.
All right, so it's gone. It's gone. So if we look back at our ice table, or more properly our equilibrium equation, okay, the degree of ionization is just going to be the concentration of formate ion at equilibrium, in other words, x, divided by not the equilibrium concentration of the starting acid, but the initial concentration. It's going to be x divided by 0.1, right? So again, it's going to be the concentration. This is how much dissociated divided by what we started with, which is 0.1, not 0.1 minus x, right? So let's do that on this board here. So I'm just going to write DOI, degree of ionization, equals concentration of formate ion at equilibrium divided by the concentration of the acid at the beginning. So I put a 0 for initial conditions. right? It's, again, important to remember they're not both equilibrium conditions, right? So then I just plug in our values. We saw that this was 8.5 times 10 to the negative fifth, and the starting concentration of the free acid was 0.10, right? And so we just get out the calculator, and we don't even need a calculator. That's going to be 8.5 times 10 to the negative fourth, all right? And if we wanted to turn that into percent ionization, we just multiply it times 100.
Raymond, do you keep freezing?
Keep freezing? Let me see if there's anything if there's any other. Usually that's when I have too many. Okay, hopefully it'll go a little better now. I actually had two windows open on the second computer that were accessing the internet. I just closed those. All right, so let's just back up here again, since I don't know where we missed, but the degree of ionization again is the equilibrium concentration of the formate ion divided by the initial concentration of the free acid. Okay, equilibrium concentration there and the starting concentration of the free acid. Okay, so we just plug the numbers in, right? So this was x over 0.1, and we solved for x was 8.5 times 10 to the negative fifth. Okay, that's the equilibrium concentration of the formate ion. Just divide the two, we have our answer. Okay, now, if we wanted percent ionization, we would just multiply that times 100. Okay, multiply it times 100. And we see that the percent ionization here is less than 1/10 of 1%. Right? Again, if we did this in terms of percent ionization, 1/10 of 1%. So why is it so low? And the answer to that is Le Chatelier's principle. Okay? If we didn't have any of this here, we know that the more of the free acid would dissociate. But we've added some hydronium ion in initially. So the equilibrium is going to shift this way, right? Going this way does not favor ionization of the free acid, right? The equilibrium shifts this way. So it makes more of the free acid. Some of the hydronium ion will recombine with some of the formate and reconstitute the free acid, and of course a water molecule. Okay? Any question here? And if we wanted the pH of the solution, we could just do this, and there's the hydronium ion concentration. Okay? I mean, the hydronium ion concentration is effectively equal to the starting concentration of the hydrochloric acid. So it would be what? Whatever the log of 2 times 10 to the negative first is. Okay? Any questions here? Any questions? Again, there's many twists on these ice tables, and I warned you about that at the start of when we did the very first one. Right? Many, many different twists on the ice table. And then the next exercise, right, is going to be very similar to this, but instead of adding hydrochloric acid, you know. Okay. Lost you, huh?
Yeah, you did.
Okay, everybody here?
I think so.
All right. So I was just saying here that I warned you when we first started doing these ice tables that as we progressed deeper into the chapter, that each section would add a new twist on these ice tables. And so we're seeing one here now. Okay, the next exercise, the example and exercise that goes with it, it's going to be very similar to this, but instead of adding acid at the beginning, we're going to add the ionic salt. Right? So in this problem, it would be like this being 0 and this not being 0. That's what we're going to see in the next problem, if I remember correctly. Okay, any questions before we move on? Any
No.
questions? Oh. Okay, so let's take a look at, let's see here. So the next example, 1610. Okay, so I'm not going to do this problem, but we're starting out with 0.1 molar acetic acid and we're mixing it with sodium acetate. Okay, so again, this would be 0 and this would be non-zero. Right, but we're going to do the exercise that goes with it. Okay, so let's look at exercise 1611. Okay, so we have, we can use the same ice table. 1 liter of solution is prepared by dissolving 0.025 moles of formic acid and 0.018 moles of sodium formate in water. Right, so this is nice. They made it a 1 liter volume. All right, 1 liter volume of solution. So the moles that were given there are equal to the molarity. Okay, because remember, in an ice table, you have these entries are molar concentrations, not moles. And we're asked to find what is the pH of the solution. Right, so 0.025 and 0.018. So we can pretty much leave this up here. All right, so there's what we're starting. There's our equilibrium equation, right? Same as in the last problem. Okay, now our values in the ice table, and if I remember correctly, this is 0.025 because we have that many moles in 1 liter of solution. So the number of moles is equal to the molar concentration. And we have 0.018 moles of sodium formate dissolved in that same solution. Right, so we have 2 chemicals in that solution, and the concentration of hydronium ion is 0. 0. Okay, does everybody understand so far? Again, remember the sodium formate, any compound, ionic compound that contains sodium ion will completely dissociate. Right, will be a strong electrolyte. Any compound that contains sodium ion or potassium for that matter, without exception, completely dissociates. So the starting concentration of the anion is just equal to the starting concentration of the sodium salt. All right, so what's going to be the change here? Well, some of this is going to dissociate. So minus X plus X plus X. Okay, simple enough. Then at equilibrium, 0.025 minus X plus X plus X. All right, plus X. All right, so now we can just set up an expression for the equilibrium constant. So let me just erase the other big board here. And I'm going to do it. Everyone have this ice table. All right, I hope we're not going to lose again here. Been getting messages all day, the bandwidth is low. All right, so we can set up Ka is equal to the hydronium ion concentration, same as before, times the concentration of formate ion, divided by the concentration of the free acid. Okay, products over reactants. Now, we just plug in the values from the ice table. And let's see, the hydronium ion is X at equilibrium. And this is, I never filled this one in, 0.018 plus X. Never filled that one in. So please add that entry to your ice table. Okay, because that concentration is going to go into our expression for the equilibrium constant. 0.018 plus X, and then the concentration of the free acid at equilibrium is 0.025 minus X. And again, we're going to do our little test, Ca over Ka, and see if it's bigger than 100. So I'll come over to this side to do that. So Ca over Ka equals 0.025 and what was the 1.7 times 10 to the negative fifth, right? The Ka for the acid?
4.
4?
Wait,
Thank you.
yeah, -4.
Okay. Now we just get our calculator. That's going to be bigger than 100. Well, maybe not. Yes. Oh, just by this slightly. So that equals 147. Right? So not much bigger than 100, but nonetheless, it is bigger than 100. So we can go ahead and drop this minus X and that plus X. Right? So on the next line, I'm going to proceed to do that. Ka equals 0.018 times X divided by 0.025. Okay, so now we can write, let's isolate X here, equals 0.025 times Ka divided by 0.018. Okay, and again, I have run out of room, but I have this over here. So we're going to bring this up to here. So we'll plug in the value for Ka. So X is equal to 0.025 times Ka, which is 1.7 times 10 to the negative fourth divided by 0.018. Okay, let's see, what was it we were actually asked to find here? The pH of the solution. All right, so now we get out our calculator. So 0.025 times 1.7 double E4 negative equals divided by 0.018 equals. We'll throw that in the scientific notation. In here I get 2.4 times 10 to the negative fourth. 2.4 times 10 to the negative fourth. All right? Now, they don't ask us to calculate the degree of ionization, but the degree of ionization would just be this, which is, actually, no, yeah, it would just be X over 0.018. Okay? Now, we're asked to calculate the pH. So we have to see how this X relates to the hydronium ion concentration from our ice table, right? Does everybody have this here? Everybody has this, right? 2.4 times 10 to the fourth negative. I'm going to put this into memory and clear the other memories. Okay, so again, we know what X is. How does that relate to the equilibrium concentration of the hydronium ion? Well, it's equal to the hydronium ion equilibrium concentration. So if we're asked to calculate pH, pH is equal to negative log hydronium ion concentration. Okay, and this X is the hydronium ion concentration, but we just calculated X. Negative log and it was 2.4 times 10. Let's see, I have it here in memory, times 10 to the negative fourth. All right, so there's the pH. Get out the calculator. All right, so I have this in my first memory, so recall 1 log negative, and I get 3.6. 3.6, so there's the pH. All right, and let me just check that since I have that one worked out already also. Yes. Okay. Any questions here? So we're probably going to get one problem like the first one and one problem like this one. Okay. Again, it's just one extra little twist on the ice table. Okay, you can see how important these ice tables are because they allow us to do a lot of different things. All right, the most amazing one will be in the next section. Okay, do we have any questions here? Any questions or comments? All right, so we're all experts on common ion effect. And we can use this common ion effect to prepare a rather amazing solution. And without this next section, none of us would be here to talk about it. The next section is on buffers. So what is a buffer?
Buffers.
A buffer is a solution that can withstand large additions.
Sorry, Raymond.
Sorry?
Sorry, I didn't know.
I lost you again?
Don't worry about it.
I lost you again?
No worries.
So what is a buffer? A buffer is a solution that can withstand very large additions of either hydronium ion or hydroxide ion. In other words, large additions of acid or base. Right? It can withstand large additions of acid or base, resulting in just very small changes in the pH. Right? This is a rather amazing thing. Right? So we can increase the hydronium ion maybe sixfold, or not sixfold, 6 orders of magnitude. So we would, so 6 powers of 10, a million. Right? We would expect the pH to change by 6 units. But we'll see that the pH will hardly change at all. This is actually a rather amazing type of solution. Okay, and as it turns out, almost every biologically reaction inside cells can only occur within the narrow pH range. So our cells are buffered. All right, our blood, for example, is buffered. All right, there's a carbonic acid. When we breathe in carbon dioxide, okay, when we breathe in oxygen, it gets converted into carbon dioxide, and we think we breathe all that carbon dioxide out, but we don't. Some of it stays in our blood, and there's a carbonic acid carbonate buffer that carefully controls the pH of our blood within just a few tenths of a pH unit. If our pH of our blood goes outside that little narrow range, you're going to be sick, and if it gets too far out, you're going to die. Right? So these buffers are very important. All right. So if we take a look at the figure on the bottom of page 567, we have a little cartoon here. I'm going to grab a seat for a moment. Okay, so we have this little cartoon. We have this beaker with 3 molecules of the intact acid and 4 copies of the free acid and 4 copies of the conjugate base of the free acid. Okay, so again, the gold ball with the little blue ball attached is the free acid, and the gold balls by themselves are the conjugate bases, okay, that have had the proton removed from the free acid. and we look on the left-hand side, we can add hydronium ion, right? If we add hydronium ion, typically you would expect all of the conjugate bases to get protonated and be converted back into the free acid, but that doesn't occur. Only one of them, or I guess in this case, two of them get protonated. The other two do not. On the right-hand side, we look and we see we add a strong base, hydroxide ion. And there, okay, adding hydroxide ion, we would expect the protons to be removed, the acidic protons to be removed from the free acid. In other words, in the right beaker, we would expect none of the little blue balls, the hydrogens, to be attached to the gold balls, right? But in fact, we see that only two of the protons are removed, and the other two remain attached to the conjugate base, right? So, in other words, adding strong base, adding strong acid only change the pH by very small amounts. Okay, and we're going to find out here towards the end. Now, we're going to start this section with by doing this with ice tables, but then we'll see that it can be done with a very, very simple equation at the end. I don't know that we'll have time to get to that today. If we take a look at the figure on page 568, okay, so we have a pH curve here, right? A pH curve for a buffer solution. And we see that in the central portion, the pH curve is relatively flat, And we see here that at the 0 position, that's where we have added neither, that's just the composition of the buffer solution. Then to the left, we're adding moles of hydronium ion. All right, you would expect the pH to drop dramatically, but in the buffer range, in that orange box, that's the range over which the buffer actually works, okay, the pH only drops a little bit, okay, just drops a little bit, not even a full pH unit. Conversely, on the right-hand side, we're adding hydroxide ion to the buffer solution, and we would expect adding concentrated hydroxide ion for the pH to rise dramatically, right? But it doesn't. It only rises, again, not even a single pH unit, right? So this is actually quite amazing, right? Actually quite amazing. All right, so how, let's take a look here. Let's see here. So let's take a look at exercise 1612. Okay, now I should mention here, let's go back to the example 1611. So I'll just read that out loud. Instructions for making up a buffer say to mix 60 milliliters of 0.1 molar ammonia with 40 milliliters of 0.1 molar ammonium chloride. Notice, okay, that the second compound here, the second solution, is the conjugate, contains the conjugate acid in the form of a salt of the free base in the other solution. Ammonia is the free base. Okay, here, let's just write that out just to refresh our memories here. NH3 plus water, so it's a weak base, gives us ammonium cation plus hydroxide ion. Right, so this is the conjugate acid of the base. Right, so notice that the buffer solution contains both the base and the conjugate acid of the free base. Okay, and that's always how you're going to set up a buffer. It will be the base and its conjugate acid, or an acid and its conjugate base. So hopefully we'll see examples of both of those here right now. So in this exercise, or sorry, in the example, we see a buffer solution that contains a free base and its conjugate acid. I'm not going to work that one. You can work through that yourself. We're going to take a look at exercise 1612, where instead of beginning with a base and its conjugate acid, we're going to begin with an acid, in this case, acetic acid, and its conjugate base, acetate anide. All right? So let's proceed to do that. I should mention, before we get started here, okay, I will tell you that in practice, right, for you budding chemists and biologists, right, so if you work in biology, like molecular biology or something, or biochemistry, you do a reaction, it has to be in a buffered solution, okay, because quite often enzymes only work over a narrow pH range. So you have to have this solution buffered, right? I used to try to grow protein crystals or DNA crystals, right? Sometimes a certain protein will only crystallize within a narrow pH range. So those solutions are always buffered, okay? Anything in biology is a buffered solution. Let's see, so does any biologist ever do the calculation that we're about to do? And the answer to that is no, right? No. Because just as was indicated in the problem for the example there, example 1611, it says instructions for making up a buffer. So they have reference books. And a very popular one when I used to do research was Data for Biochemical Research. And there was like 75 pages of that reference book that was nothing but recipes to make up buffers. So if you notice there in that example, it's 60 mils of the base, NH3, and 40 mils of the conjugate acid, the ammonium chloride. 60 milliliters plus 40 milliliters makes 100 milliliters. So typically these recipes, these tables for making up buffers, so you're going to mix some volume of the base, some volume of the conjugate acid, but usually those two volumes when added together will be 100 milliliters, as in that example there, as in that example. So let's look at our exercise. What is the pH? And there it is, 30 milliliters to 70 milliliters, 100. So if you're a biologist and you have to make some solution that requires pH, I don't know, 7.6, right? You just look in the table and find out, okay, I'm going to mix this many mils of the free base, this many mils of the conjugate acid, and that will give me a pH of 7.6, right? If you want pH of 8.2, then you're going to change those concentrations a little bit, but it will all be tabulated there. You don't have to do this calculation. Whoever made the reference book has already done that calculation for you, right? But you should understand where these numbers come from. All right, so we're asked, what is the pH of a buffer prepared by adding 30 mils of acetic acid and 0.2 mils of sodium acetate? So let's get an equilibrium equation for that. So acetic acid, I'm going to rewrite, I like to write my acids, organic acids like that. All right, plus H2O gives me hydronium ion plus acetate anion. Okay, now, I think I had you guys do dilution equation at one time, right? Because if we take a look here, what is the pH of a buffer prepared by adding 30 mils of 0.15 molar, all right, to 70 mils of 0.2 molar. So that 30 mils of acetic acid is being diluted to 100 mils. Similarly, the 70 mils of the 0.2 molar sodium acetate is being diluted to 100 mils. So we have to use the dilution equation to calculate the new molar concentrations that we will then plug into our ice table. Does everyone understand that? Okay, so it says the acid concentration is 0.15 molar. We can't write that in here because that 0.15 molar is being diluted to 100 milliliters. So we're going to have a new concentration there. So let's go ahead and do that. So we have to do it for both the acetic acid and the sodium formate. Let's do the acetic acid first. And if you remember, the dilution equation is C1V1 equals C2V2, right? And for the acetic acid, C1 equals, what was it, 0.15 molar? Yes. 0.15 molar. The first volume is 30.0 milliliters. Second set of conditions. Concentration is unknown. That's what I'm trying to figure out. And the second volume is, 100 milliliters after we dilute it. Does everybody understand what I'm doing? If you don't understand, you need to speak up here. We're starting with this volume of this concentration of acetic acid. But after we add the 70 milliliters of sodium formate or sodium acetate solution, the volume's not going to be 30 milliliters anymore. It's going to be 100 milliliters. So therefore, the concentration will no longer be 0.15 molar. We have to calculate what that new concentration is. Right? So here's the dilution equation. And I always like to look here and put my unknown on the left. Right? Put my unknown on the left. Right? So let's see. Check off what we know and what we don't know. Don't know that. Know that. Know that. Know that. So I need to move V2 over to the other side. Get rid of it there. Underneath, write what's left. C1V1 over V2. Go ahead and plug in from over there. So C1 is 0.15 molar. V1 is 30 mils. Actually, we should have changed these to liters because we want, actually, no, sorry, we don't need to do that. Sorry, we don't need to do that. You'll see why in a moment. Okay, divided by the second volume, which is 100 milliliters. Okay, and this is why we did not need to convert to liters. Because if you look right here, the milliliters cancel. The milliliters cancel. So it's just an extra work to convert it into liters. So my final concentration is 0.15 times 0.15 times 30 equals divided by 100, and it had better be less than 0.15. So 6.75 times 10 to the negative third molar. The only unit left is molar. Right? I'm going to calculate that one more time just to make sure that it's right. 0.15 times 30 equals divided by 100 equals.
I got 0.045.
Yeah, that sounded kind of small. This is why we do every calculation twice. Every calculation twice. So 0.045 molar.
Oh, molar.
Molar. Right? Because the only unit left here is molar.
Okay.
Again, this is why we do every calculation twice. So we can go ahead in and write that value up here and make an ice table. And the starting concentration here is 0.045, not 0.15. Does everybody understand now? Okay, then we need to do the same thing for the acetate ion. They came from the sodium formate. We're going to do the exact same thing. All right. So you see how kind of all these things come together. I think I mentioned to you guys when we started all this, the chapters 14, 15, and 16 are Very, very useful in the laboratory, whether you're in chemistry, but especially in biology. All right, so let's take a look. For the sodium formate, or sodium acetate, we had 70 mils of a 0.2 molar solution. So C1 equals 0.20 molar. The volume is 70.0 milliliters. And C2, we don't know that concentration, and V2 is 100.0 milliliters. Okay, now let me just say one thing about when you're doing these dilution problems. They're extremely simple. Believe it or not, I just did these with the high school kids. Okay, but the important thing though is you have to have the right concentration with the right volume. All right, the right concentration with the right volume. And if you read that problem, it says 70 mils of a 0.2 molar solution. Those two go together. The final volume is the 30 from the acetic acid plus the 70 from the sodium formate to give me 100 milliliters. You don't understand that, you need to say, Raymond, I don't understand that, make it clear. Right, and then we're going to calculate the new concentration after we mix the two together. So my unknown is in my second set of conditions. So I'm going to put that on the left-hand side. Check off what we know and what we don't know. Let's see, don't know C2. I know V2, C1, and V1. So C2 is in the numerator, not by itself. I need to move V2 over to the other side, where I can get rid of it on the left-hand side. Underneath, write what's left. C1, V1 divided by V2. Okay? C2 is in the numerator and it's by itself. We can go ahead and plug the numbers in. So C1 is 0.20 molar. V1 is 70.0 mils. And V2 is 100 mils. You can cancel the milliliters. And my only unit left is molar, which is what we expect a concentration to be in. All right, so now we get out our calculator. But now my answer had better be less than 0.2 because I'm diluting it. So 0.2 times 70 equals divided by 100 equals. And I get 0.14 molar. Right, so I'm going to write that in red so it stands out a little bit. Hopefully you guys can see this. 0.14 molar. All right, 0.14 molar. So we're going to put that in. Remember, this is for the sodium acetate. All right, 0.14 molar. So I'm going to take this and write that up here. All right, and my starting hydronium ion concentration is 0. 0. Does everybody understand what we did here and why we did it? Okay.
Yes.
Both solutions are being diluted when you mix them together. All right, so what's the change here? Well, this is going to be minus x plus x plus x. All right, so again, just to notice there's a common ion effect here. Common ion effect. All right, so equilibrium 0.045 minus x plus x 0.14 plus x. All right, so we can go ahead and set up an expression for the equilibrium constant. Set up an expression for the equilibrium constant. All right, so let's proceed to do that. Let's see here, I'll pick black. So Ka equals hydronium ion times acetate ion divided by acetic acid. And from our ice table, well, let's see, hydronium ion is simply X. And this is 0.14 plus X. And this is 0.045 minus X. All right, so we're going to have to do our little CA over KA. All right, so we go back and find the dissociation constant for acetic acid, and it's 1.7 times 10 to the negative fifth. So Ca divided by Ka and this is 0.045. That's going to be way bigger than 100. Okay, it's 2,647. Right, so way bigger. Whoa, way bigger than Ka. Right, way bigger than 100. So we can neglect these two X's here. All right. I just want to check one thing here real quick. Yes. So I'm going to rewrite this, dropping the plus X and the minus X. So 0.14 times X divided by 0.045. Okay. So I'm going to solve this for X. So 0.045 times X times Ka divided by 0.14 equals X. Right? Equals X. Now I've run out of room, so I'm going to bring it up here. All right. So now X, plug in the value for Ka, X equals 0.045 times 1.7 times 10 to the negative fifth divided by 0.14. Okay, actually I'm going to put approximately because we made that Ka over C, or Ca over Ka approximation. So 0.045 times 1.7 times 10 to the fifth negative equals divided by 0.14 equals, and I get 5.5 times 10 to the negative 6. 5.5 times 10 to the negative 6. Now remember, that's our X, and I'll give you a chance to copy that down. So we have to see from our ice table, how does that relate to the concentration of the hydronium ion? So as soon as everybody copies that down, we'll look at the other big board and check that. And if I remember correctly, we'll see that the two are the same. Okay, everybody have this? Everybody has?
Yes.
All right, so X, this is the value for X. We're looking for the pH of the solution. So we want the hydronium ion concentration. Well, X is the hydronium ion concentration. X is the hydronium ion concentration. All right, so we can come back here and calculate the pH now. So pH equals negative log hydronium ion concentration. All right. Negative log We're going to plug in the value for the hydronium ion concentration, which was on that other board, the value for X. 5.5 times 10 to the negative 6. Right? And that's equal to 5.3. Okay, and I checked, that is what I had before.
Hey Raymond, are you rounding from what you get on the calculator? So for instance, I got 5.46 times 10
Yes,
to the
the
6.
reason here is I only have 2 digits here. All right, so my answer should only have 2 digits. Actually, if I remember correctly, earlier in the book it said 2 digits here means you should have 2 digits in your pH, 2 decimal digits in your pH. Let me just check the answer in the back, and I'll bet that that probably is the case here. 16, 12. Yeah. So we should have left that with, here. This should be 5.26.
Yeah, that's what I got.
But the concentration that we calculated before, here, this here, who's ever asking that question, should only have two digits here, 5.5, because I have two significant digits here and 2 here and 2 here. Remember, your final answer can only have as many significant digits as the smallest number of significant digits in whatever you're multiplying or dividing.
Okay.
So I have 2 here, 2 here, 2 here, so I can only have 2 here. But when we do this here, when we calculate the pH, somewhere back, I think it was the previous chapter, chapter 15, it said how many decimal digits should you have in a pH calculation? And if I remember correctly, it said you should have as many decimal digits in your pH as you have had significant digits in the hydronium ion concentration. So I have 2 here, so I should have 2 decimal digits in my pH value.
Okay.
Okay? Any other question there? Any other questions? Because we're about out of time here. All right. So I'm going to assign you 3 problems, 1 of each. We did 3 examples, 3 exercises. So I'm going to assign you 1 problem on each. If you don't get them done by Thursday, not a big deal. These take a little more time, right? You got to be careful, right? You really have to be careful. Make sure you're using that approximation CA over KA or CB over KB, okay? Let's see, what else to be careful of? Make sure you have your ice table set up properly, right? Make sure you have that set up properly, okay? And by now, you shouldn't have, this should be second nature, writing down an acid or a base dissociation reaction, right? It's always something reacted with water to give you either hydroxide or hydronium ion in either the conjugate base or the conjugate acid, whatever you started with over here. Right? That should be second nature to you by now. Right? Same with setting up an ice table. Again, be careful. We had to do the dilution here. Right? So in a buffer, there's always going to be dilution because you're mixing 2 solutions together. Right? You're mixing 2 solutions together. So there's always going to be dilution. Okay? Because again, you're looking up in these recipes. Okay, so you have all these solutions made up on the shelf, and it says mix this many mils of this with this many mils of that. Okay, so it's not like you're making up these solutions fresh every time you need to make a buffer solution. You just go grab a stock solution off of the shelf and you mix them together and you get your appropriate concentration. Let's see, where else? Don't forget, I think it was the second problem we had to. No, we didn't have to recalculate the molarity because they gave us the quantity of chemical in moles, but then they said it was dissolved in 1 liter of solution. And I think, Miranda, this is a question you were asking me a couple problem sets ago. You have to be careful of that. Because if they had said three liters of solution, then you have to take those moles and divide it by 3 liters to get the molar concentration. So you got to be careful. Read the problems very, very carefully. Moles and molar are not the same thing. Molar is moles divided by liters of solution. Okay, so you got to be extra careful in these problems. Okay, extra careful. They're not that hard, but there's a lot of little places where you can screw up and make a mistake. A lot. Okay, so I think I've warned you of all the sufficient pitfalls here to be on guard for. Okay, and again, these are all just another twist on an ice table, right? And here we used, so in a buffer solution, you're using the common ion effect, right? So I think what we will do next class, we'll finish this section on buffers, and so we'll calculate the pH. Okay, so you have this solution now. What happens when you add some hydrochloric acid to this? What happens when I add some base to this buffer solution? And we'll calculate the pH, and we'll see it'll change a very, very small amount, even though we're adding a good bit of hydronium ion or hydroxide ion. That's the whole point of a buffer solution. Whole point. Then we'll take a look at the Henderson-Hasselbalch equation, which is to do this calculation without having to do all this. It's much, much simpler. You do it in just a couple lines. The 3 problems I'm going to assign you now, I want you to do them with an ice table, just like we're doing now, right? And then I think that will help you to appreciate the Henderson-Hasselbalch equation even more, which we'll get to next class. All right? If you want to read ahead a little bit, it should be on just like 2 more pages from where we're at right now. You can take a look at the Henderson-Hasselbalch equation. But again, I don't want you using that to solve these problems that I'm going to give you today. Okay, any other questions? Don't forget to take a look at that equilibrium constant lab. I haven't done the calculations. We're going to need to do that. I'm just going to have to make some time to do that. Any other questions? Let's see. I'm going to stop recording here. I think everybody's here anyway.